Hi. Let's continue our study of the string equation. Today it will be a more theoretical lecture. So consider the string equation u tt minus u xx equals 0. So what we know, just for simplicity, suppose that x and t in the whole line. Without any boundary, any initial condition, just this equation. Then what we know? We know the following thing, that every solution u of xt of equation 1 has the form u of xt equals v of x plus t plus w of x minus t. And conversely, any function u of xt of the form u of xt equals v x plus t plus w of x minus t is a solution of 1. Clear that these are different statements. We started from solution and got this form, or we started from this form and made sure that this is solution. Now I did not say much about this function v and w. If you want to have solution in a literal sense, then you should be able to substitute these functions into the equation. So this means that they should have continuous derivatives of first and second order. Otherwise, it's not clear what does it mean to substitute here. So here v of x and w of x are function having two continuous derivatives. No, they continuous themselves have continuous first and second derivatives. Then we can take the sum, this combination, and we are able to substitute it into the equation, and we'll have solution. So in this case, u of xt is called classical solution of equation 1. So classical solution is solution regular enough so that we can substitute it into the equation, and every term has the sense. So if equation of second order, then the function u should have all derivatives up to the order 2 continuous functions. Then we can substitute it and be sure that the equation is satisfied at every point. However, we considered as examples also some functions which are not in C2, and moreover they are not even differentiable. So for example, we consider the function, so in examples we had functions like this. No, let me draw a picture of this function. It is a graph of the function. It is x, so it is function u of x. For example, this function. So this function is continuous, but it is not continuously differentiable. So it breaks down at these sharp points where the derivative is discontinuous. Yes. So let me say v of x, or we consider the function something like this, or like this, and so on. Nonetheless, we substituted these functions in this formula and said that it is okay, this is solution. Now, in particular, we considered I like this example. Let me draw it again. The motion of guitar string. So consider the initial condition. This form, it is a piecewise linear function. It goes linear function from 0 to L over 2. And then another piece which is linear from L over 2 to L. It satisfies 0 or Dirichlet boundary conditions at the end points. And this corresponds to the guitar string, which we took in the middle, pulled it aside, and then let it go, released here. So how does the string behave? It is very beautiful. It is t equal 0. It is for some positive t. And so it goes down, and then it will at some moment which is L over 2, t equal L over 2, it is the function is 0, but the time derivative is not 0, so it keeps going down. So then we have this picture, and then at t equal L we have this picture. And then this steno, it is symmetric. It is like this. Then it starts going up. Yes. Then it reaches it is 0, but the time derivative is not 0, so it has some velocity. It is t equals 3L over 2. Then it is almost done, and then it returns to the initial position. It is t equal to L. So period is 2L. And then it goes, we return here, and then we go again the new cycle. Yes? So here it is quite a beautiful solution, and even beautiful to listen to it, but it certainly is not solution, because the function is not even not continuously differentiable. So how can we accommodate this solution in our theory? So we want to call it solution, but in the literal sense it's not solution. So it looks like a contradiction. So to overcome this contradiction, we first use a good word and call this solution weak solution. Weak solution, so as opposite to classical. So classical solution is a smooth solution, or called strong solution, and this solution is not a classical solution, it's a weak solution. And now let me give you a definition. What is a weak solution? No, in general, weak solution is a favorite subject of today's theory of partial differential equations. Yes, we mostly study weak solutions because they are, I would say, overwhelmingly more numerous, and they have distinct physical meaning. So let me give you a definition. U of xt is called a weak solution of one is the string equation of string equation if there exists a sequence of smooth classical, better to say not sequence, but family of classical solutions which I denote U epsilon of xt, such that module U of xt minus U epsilon of xt less than epsilon for all x t in the domain where the equation is solved. Now, in this case, this domain is just the segment from 0 to L. So it is finite domain. What does it mean? This solution is not regular. it has this discontinuity. So let me replace this function by a function where we just round this corner. Yes? Now, how can we express it analytically? Now, let us consider example. I wanted to isolate this one point. So suppose our function u of x, let me forget for a moment about the t, equals, say, module x. U of x equals module x. This is the graph. And let us consider the function u epsilon of x. One moment. Square root of x square plus epsilon square. Yeah? Now, the graph of this function is a hyperbola. It is hyperbola like this. This hyperbola. So these two branches of graph of module x, this and this, are asymptotes. This hyperbola tends to this or this line when x goes to infinity, and here the value of this function is exactly epsilon. When x is 0, this is the u epsilon of x is epsilon. Yeah. Now we see that this function is already close to ux as module x if you go farther. But here it can be at the distance epsilon. But if you consider smaller epsilon, we'll have something like this. Yeah? You see it becomes closer. So when epsilon goes to 0, it goes closer and closer. Yeah? So we can, as we in mathematics say, approximate the function u of x by a smooth function u epsilon of x, where epsilon is parameter. it is how close we are approximating it. No, I would say rationale about this is that if you consider a function like module x having discontinuity of the derivatives and look from some distance, then we don't see a big difference between this function and function which is with a little bit rounded corner. Yes, so they are close. And so this is one of possible definitions of weak solution. So weak solution is a function which can be approximated by classical, smooth classical solution. Yes, that's it. To justify it, we should prove, usually, in this case it is obvious, that if we take, say, a little bit different approximation, then the result will be more or less the same. Yeah. Let us keep to this definition. with this definition, we can see that our solutions, for example, this function, like this. So this function is a weak solution. Say it is v of x, and we consider a function u of x t equals v of x plus t. Yeah. So if you somehow smoothen this function this way, then we have a smooth function, which is close to v. So this is v epsilon of x. Yes. And then we consider u epsilon of xt equals v epsilon x plus t. And this will be a solution which approximate this solution, u of xt. So this means that this is a weak solution. Here is one, I would say, weak point that we could draw something here, but if the function is not so simple, if it is some more tricky continuous function, then how can we be sure that there exists such a function, such a smooth function which is close to it? This is a good theorem of analysis, and we will need it, this theorem, and we will need construction which is used in this theorem more than once in this course. So I have to formulate and prove this great theorem. No, better to say, I formulate a theorem which is not related at all to the subject of equations. It is just pure analysis. The following theorem. One moment. For this theorem, I need a new pen. Let f of x is a continuous function on a segment AB. From x, it is x between A and B. The endpoints are included here. So let f be a continuous function. Then for any epsilon, there exists a function f epsilon of x, which is infinitely many times differentiable on the segment AB. This means that it has derivatives of all orders continuously, such that module fx minus f epsilon of x less than epsilon for all x between A and B. So So this is the theorem. One moment, I have to find another pen. Or in other words, any continuous function can be approximated by a smooth function. Smooth means infinitely many times differentiable. It is true for any continuous function. No, it is a deep, great theorem, and I wanted to prove it again because I will need not only the theorem itself, but the construction of this approximation. So the proof is given epsilon, I construct this function f epsilon. So in the proof I use a very useful device called modifier, or I would say smoothener. Something, some operation, some device which is used to make a function smooth. So we somehow take the function and produce other function which is close, epsilon close to this function and smooth. So it requires modifier. So what is modifier? It is the following function. Phi of x in C infinity, yes, having satisfying the following condition. First, phi of x is infinitely many times differentiable function. Second, phi of x equal 0 for all module x more or equal than 1. 3. Phi of x more or equal than 0. And 4. Integral, no, the function is 0 outside the segment minus 1, 1, so the limit phi of x dx limits we can write freely from minus infinity to plus infinity. Yes, because anyway it is exactly 0 outside a finite interval. So this integral is 1. So this function looks like this. It is x, it is phi of x. It is this function looks like this. So here it is positive, here it is 0, and everywhere it has all continuous derivatives. So this is very important. No, if you wish, I use phi of minus x equals phi of x. So phi is an even function. Sometimes it is useful. Now the next is construction of the function itself. construction of this function phi of x. Now we construct it in a couple of steps. The first step, we define function psi1 of x given by the following formula: e minus 1 over x when x is more than 0, and 0 x is less or equal than 0. This is function psi1. So what we can say about this function? First of all, this function is for positive x monotonic. When x goes to 0, so psi1 of x, if x goes to infinity, then this goes to 0, so this exponent goes to 1 as x goes to plus infinity. Psi1 of x, if x goes to 0, then 1 over x goes to infinity, minus it goes to minus infinity, so it goes to 0. 0 as x goes to 0 plus. 0 plus means that it goes to 0 from the right, from the positive direction. So this means that psi1 of x is a continuous function on the whole line. It is the first. Second, this function is obviously infinitely many times differentiable for positive x and for negative x. But what about the point 0? Let us find the derivative. Psi1 prime of x equals 1 over x square e minus 1 over x. So what can you say about this? When x goes to 0, one moment, let me draw the graph of this function, psi1 of x, and here it is 0. So we are concerned with this point. When x goes to 0 from the right, this goes to infinity, this goes to 0. But they know from the calculus or from analysis that exponent goes to infinity faster than any positive degree of x. Or exponent goes to 0 when here we have this exponent. This goes to 0 faster than this goes to infinity. Yes? So this means that it goes to 0 as x goes to 0 from the right. Yes? Now we can find psi1 double prime of x equals minus 2 divided by x cubed plus 1 divided by x to the 4 e minus 1 over x, and also goes to 0 if we are going to, and so on. So derivative of order n of x. No, we have to continue, we have to differentiate this times exponent and then differentiate this, and after all we'll have here some polynomial of degree 2n, yes, here one of one moment. Yes, it is of 1 over x times e minus 1 over x. And by the same reason, this function goes to 0 faster than this function goes to infinity when x goes to 0. And so it also goes to 0 as x goes to plus 0. And what does it mean? This means that this function psi1, we can continue this derivative here by 0, yeah, because it goes to 0 from the right, and of course goes to 0 from the left. So, and the function is continuous. So we define it by 0 here, and so we have, let me continue here, that psi1 of x is in C infinity. So this way, yes, I have this function here. So we constructed a function which is in C infinity, which is non-negative, and which is 0 for x negative. Yes? Now we define function psi2 of x equals psi1 of x plus 1 times psi1 of 1 minus x. What is this? This is minus 1, this is 1. So the first factor is a function which is 0 for x less than 1. Then it grows, and then goes to 1. The second factor, it is 0 for x more than plus 1. Then it grows when we go to the left, and then goes to 1 here. And if you take the product, we'll have something like this. Here it is, this function, which is called psi2 of x. And psi2 has the properties. First, it is C infinity. Psi2 more equal than 0. Psi2x equal 0 to the left of minus 1 to the right of plus 1 for module x more than 1. And psi2 of minus x equals psi2 of x. And the only thing which is lacking here is the last requirement. Integral of this function psi2 is 1. So we define at last phi of x equals psi2 of x divided by integral psi2 of x dx. Now let's write from minus infinity to plus infinity. Or from minus 1 to plus 1. I will write better like this because it's correct. Now, so integral of this equal integral of psi2 of x dx divided by integral of psi2 of x dx. So integral phi x dx from minus infinity to plus infinity equals 1. So we have all necessary conditions to define phi of x. Okay, so let us make a small break, and in the second part I will tell you how to use this fine function to approximate any continuous function. Have a good time for a while.